Direction Independent U-Function based sensorless control of BLDC motor. Salient features are introduction, modeling of VSI-fed BLDC motor drive, proposed sensorless BLDC drive, and simulation results, conclusion, references. Brushless DC motors are very high efficiency and high torque to current ratio and high power rating motors. These are fed from variable voltage, variable frequency VSIs. They are communicated through the Hall sensors and encoder-based positioning schemes. Present co-initialize the milestone research using the waveform detection of induction motor. Due to the limitations of Hall sensors and encoders in terms of machine size, reliability, and noise, the sensorless schemes are preferred. Various detection-based sensorless control schemes were introduced: third harmonic detection, backing of integration, backing of zero crossing point detection, revealing diode conduction. Indirect and direct methods have the losses in filtering and detection circuit, so the performance is degraded. The PWM studies have also been used for detection of backing up, but these trap unwanted signal oscillations in torque and degrade the motor performance. Observer-based control techniques were also introduced to overcome the problems. Generally, the unknown input observer method has been widely implemented, especially in the field of fault detection. Unknown input observer assumes the back EMF information to be unknown, and the estimation of unknown value of back EMF is done with the appropriate Kalman gain filter. After estimation, various other functions, commutation function, speed independent position function, were devised. These functions are achieved in the form of train of high magnitude impulses. The magnitude and width varies as there is a disturbance in motor performance, and so the threshold cannot be appropriately determined. Uh, Performance of these methods is not satisfactory at all speeds. To overcome this problem, a simple function named zero difference point has been introduced, in which the point of two back EMFs being equal is detected and the commutation pulses are released. A simulation study was carried out and calculation of zero difference points have been taken out. Determining the threshold in ZDP method is easy and position detection is precise from this method. However, the method is not suitable for the 4-quadrant application, so this proposed function U-function has been introduced, and this is appropriate for the 4-quadrant application, in which we can use it for low to high speed operation. The estimated speed is used as feedback for calculation of U-function as well as for speed proportional current control loop. Two methods have been used for speed estimation. One is the magnitude but ripple less, and one exact direction but ripple speed. This is a voltage source inverter fed with the DC source, and this is the grounding inductance and resistances. These are the MOSFET switches. Here the phase variables are given, voltage variables in terms of phase current variables are given, and the generated torque is given by this equation. Here we can see that the back EMF and the current are in the same phase for all three phases. Proposed sensorless brushless DC motor drive. We have implemented the line-to-line back EMF estimation from subtracting one equation from another, and we get this equation for back EMF estimation. This can be written in the form of ax plus b plus fu and y equal to cx plus du. Here two phase variables IAN minus IBN are the phase to phase currents, and EAN minus EBN are the phase to phase back EMF, and these are the matrices. If we augment the matrix, then we get this matrix. So the system is being observable. The actual back EMF can be identified by this system equation. So complete observer equation is given by this matrix equation, differential equation, and which is modeled in this form. Here the depending on the DC voltage, various voltage vectors are generated depending on the switching positions, and by the line to line voltage and currents we generate the line to line back EMF, and depending on this line to line back EMF and actual speed, estimated speed, we can define the U function and virtual Hall signals, by which we can get the switching variables. Here the gain matrix is K1 K2, and the variation in the estimated quantity is given by the error in the estimated line to line back EMF multiplied by gain K2. So the derivative of the error is given by this value of the error. Observer gain calculation is given by the Ackermann's method, from where we can define the values of K1 and K2 by this equation. Different eigenvalues can be chosen for best performance considering the mutual balance between fast convergence in case of eigenvalues near minus infinity, sluggishness in the system for small eigenvalues, and sensitivity towards the noise and other disturbance for large eigenvalues. Total speed and position estimation. The line to line back EMF is given by this, and the maximum of this divided by twice of the back EMF constant. This is the mechanical electrical degree, and multiplied by 2 upon P given by the mechanical rotor speed, estimated rotor speed. Rotor angle can be given by the integration of this plus a fixed value. This is the initial angle of the rotor with phase axis A. K is back EMF constant. For the direction estimation, another speed estimation method was followed from this literature. Using both the estimations, the ripple exact speed with direction is obtained. The speed and direction independent U function has been proposed. The proposed U function has the property that it crosses the zero axis only at the actual solid state or transition edges, unlike CF and SIPF. With U functions, there is no any need of setting the threshold values. The position of the phase MMF axis may obtain wherever the derivative of U function is 0. As the reversal occurs, the back EMF polarity and sequences become opposite, so the direction normalization multiplying by speed ratio is done. This is the U function depending on all three line to line back EMFs, UAB, UBC and UCA. So comparing these relative to 0, these functions relative to 0, the virtual Hall sensor signals are obtained. Here these are the U functions, and comparing this U function to 0, we can get the Hall sensor signals. Here UCA is less than 0, then Hall sensor, virtual Hall sensor A is 1. Greater than 0, then is virtual Hall sensor A is 0. In this way we can get the virtual Hall sensors, which are exactly same as the actual Hall sensors signals. Complete drive control system. Here AC to DC converter and a PFC converter together with 3-phase DSI is fed from a rectangular 3-phase current controlled PWM based PWM hysteresis current controller based switching. Here the reference and actual speeds together with the load torque and actual electromagnetic torque are given, and this is the current limiter. A proportional current is generated here, and depending on this reference current, a rectangular current is generated, and the switching signals are given from the U function. From DC source, the three VAB, VBC and VCA voltage vectors are generated, and line currents are calculated from the phase currents from here. And these are the parameters we have simulated. Simulation results. The simulation has been done in MATLAB platform for 1 into 10 power minus 6 seconds, 1 microsecond and 0.5 second simulation time. Using the MATLAB 2011B with the motor and controller parameters as shown in table 2. Load, torque and reference speeds are changed with time as per the following table. Here we can see that initially the load torque is 3 and reference speed is minus 2000, and at 0.15 second load torque changes to 2 and reference speed changes to positive 1000. At time 0.5 second load torque is 2 Newton meter and reference speed is positive 500, and again at 0.4 second the load torque changes to 4 Newton meter and reference speed changes to 500. So the reference and actual values of speed and torque, and current are given here. The references are minus 200, 1000 and 500 RPM. Here we can see that this is the forward reverse motoring, and this is forward motoring, and here the forward braking is here, and again forward motoring here, again here. This is the phase currents which is following the rectangular waveform. Virtual Hall signals from U functions and actual Hall signals. Because the values of U function has very high magnitude as Hall transition is, so the limiter is used to show the values. So here this is the U-shaped function. Here we can see that this has the additional sensitivity at 0.173 second time comparatively to the actual Hall signals. Zoomed view shows that this is the additional pulse at the transition from negative to positive speed. When there is a positive to negative speed transition, then there is a dip in pulse at this time, at the time of transition. It can be seen that the virtual Hall sensor signals using U function gives extra short duration pulse signal that during the reversal while the sequence is same as the real Hall signals at all other instances. Also during the starting instance, the virtual Hall signals are seen performing most instrument manner and estimates the initial position. Detects this U function estimates the initial position. This is the phase current and back EMF waveforms. Here the speed of minus 1000. This is plus 1000 speed, and this is 500 of speed. So this is the back EMF waveform. Reference tracking of estimated and actual speeds. Here two cases has been considered for this minus 3000 to changes to 3000, first is 3000 and then it changes to minus 5000 rpm with 2 newton meter of load input, while in the second case the speed is initial speed is 3000 and then speed reference is changed to minus 3000 and then again positive 5000 rpm if, at 0, 0.2 and 0.4 seconds. So we can see here that actual uh, estimated speed is following the tracking the actual speed, and this has high response high response comparative with the reference speed given. This we can see in the another case. The estimated speed and actual speeds are tracking to each other. So we come to the conclusion. In the proposed work, we have proposed the U-function based sensorless control scheme or brushless DC motor. The exact speed value with direction information has been used in control loop. The line-to-line back EMF has been estimated using unknown input observer for speed magnitude calculation as well as U-function calculation. This U-function has more sensitivity during starting and reversal. Uh, the positions are stable as the solid Hall sensors. The method has been observed to be self-sustainable in the condition of the load disturbance, vibration, and step load variations. Proposed sensorless system is completely free of actual speed or position feedback, works only on estimated line-to-line back EMF. These are the references.